This is a video for AQA Discrete Mathematics, Binary Operations, Section 2.3, Abelian Groups. Well, we said that the group axioms were those of closure, associativity, identity, and inverse, and that we didn't need commutativity. However, there are many groups that are commutative. In other words, we have the idea that A combined with B is the same as B combined with A, so the order can be swapped round. And these groups are known as Abelian groups. Of course, as a group, it must satisfy the four main axioms, which are closure, as I said, unique, identity, inverse, and associativity. If it's not Abelian, then it's usually quite easy to find a counterexample to prove that although it's a group, it is not commutative. However, if commutativity is a property, then we have an Abelian group. Well, as an example of that, we've already proved that this particular thing is a group multiplication of these four numbers using complex multiplication. And then we want to decide, well, is it an Abelian group? So we need to check for the commutative. It's quite easy if you've got a KD table, because if it's going to be commutative, then it's going to be symmetric. So we can take the leading diagonal here and just check whether it's symmetric about that leading diagonal, and indeed you can see yes it is, and therefore for all elements we have the fact that A multiplied by B is the same as B multiplied by A. As a second example, let's take this set, which is the set of all 2 by 2 matrices which have inverses. So we can see that we've got the condition here that AD minus BC, i.e. the determinant, is not equal to 0. So we can find inverses of those. So we need to check first of all, is it a group? Well, the first property to check is the fact that it's closed. Well, we know that multiplying 2 by 2 matrices together produces a second 2 by 2 matrix, but we also need to make sure that we end up with an invertible matrix. Well, we know that the determinant of A multiplied by the determinant of B is the same as the determinant of A multiplied by B. So if these are non-zero, in other words, we have non-zero determinants for each of the two matrices we're multiplying together, then it must be the case that the determinant of A times B is also not equal to 0. So the matrix that we get is invertible, and therefore we must have a closed set under the multiplication of matrices. Associativity. Well, yes, and obviously it's not possible to check every single element, but we know from our work previously that if we multiply matrices together, then we do have associativity. So A, B, C is the same as AB multiplied by C. Is there an identity? Yes, the identity is the matrix 1, 0, 0, 1. So yes, that's true. And does every element have an inverse? Well, we know from, again, our previous work that the inverse of any given matrix that has AD minus BC not equal to 0 is given by 1 over AD minus BC multiplied by, we swap the leading diagonal and change the sign on the other diagonal. So this is equal to M inverse, and then we have that M inverse is equal to M inverse M is equal to the identity element that we've just identified. So we're sure now that we have a group, but we need to think about, is it an Abelian group? Well, again, from work that we've done previously, we know in fact that in general AB is not equal to BA in general, and all we would need to do is to find one counterexample so that you could easily do that to show that it's not an abelian group. So to check for abelian groups in general, then you must satisfy all of the four group properties, and then to either prove that for all elements AB is equal to BA, or alternatively find a counterexample to show that it's not true, and therefore it's not an abelian group. There are lots of examples, quite interesting examples about groups that you could look at, particularly symmetries of triangles and rectangles and such like. And there's a YouTube video that you might like to watch which actually looks at this, and there's the reference for that if you're interested. And that's the end of this particular video. In the next one, we'll be looking at the idea of generators for groups.